गुड मॉर्निंग लेक्चर लेती So, good vision. Those who are absent or were not able to attend the class. So, today again we will see what do you mean by shallow foundation. So, of the structure which transfer, a foundation is that member which provides support for the structure and its load. It includes the soil and rock of Earth's crust and any special part of structure that serves to transmit the load into the rock or soil. So these are the different types of footings. Kindly Alright. So from here itself, we are able to know. So for this shallow and deep foundation, what particular things we have to consider? So if you are considering the shallow foundation, then you can see that the depth of foundation df should be less than or equal to d, where df is the foundation depth and b is the width of your design footing. So when your depth of foundation is less than or equal to b, then you can say that you can provide the shallow foundation. And if the depth of foundation is greater than your width of footing b, then you have to go for deep foundation. So in shallow foundations we have lot of varieties. So first there is footing and another is your raft or footing. So in footing you can see we can give spread footing, stack footing, combined footing. If you go for spread footing, there are again two types. One is your isolated footing, another is strip or continuous footing. If you go for combined footing, you have rectangular footing and another is your trapezoidal footing. If you consider a deep foundation, then you go for deep footing, a pile you go for foundation, and another is your shallow foundation. So you can see that if your depth of foundation here is less than your width of footing, then you can consider this. If it is greater than your width of footing, then you have to go for deep foundation. Foundations that transmit structural loads to the nearby surface soils are spread footing. First, mat footing you have to give. Type B given by Tarzagi. Later on, it was studied and it was said that df upon b should be less than or equal to 3 to 4 meter. So, what are the requirements? So, requirements to satisfy or satisfactory foundations are safe against failure, that is your bearing capacity, should not undergo excessive displacement, that means settlements, which may lead to differential settlements. Consideration on any future influences which could adversely affect its performance. First action, scoring of the pier, foundations of the bridge, etc. It means that wherever there are snowfalls or there is having a thrust action, then the heaves are developed. Heaves means the soil will bulge out of your foundation. That is, this is your footing, this is your column, and because of this deep loading, the soil will try to travel in upward position, and here will be your bulging. That bulging is known as your heave, which is always produced in thrust actions, soaring of the piers and bridges. So you have to consider this part also. Types of shallow foundation. Spread footing, spread footing foundations, an enlargement at the bottom of the column or bearing wall that spreads the applied structural loads over a sufficiently large soil area. That is, if you are having a column footing, then whatever load is acting on that required column is there to provide that load on a surrounded soil or the soil under its loading. Next is the type is square spread footings supporting a single centrally supported column, that is the load is acting directly on a axial part of the column to the footing. Next is your rectangular spread footing. In such cases, obstacles prevent construction of a square footing with a sufficiently large base area and large moment loads are present. That is, if two columns are near to each other, then you cannot provide the square footing since the footing can overlap each other. So what you have to do is you have to consider the two columns with a single footing, that is known as your rectangular footing. Circular spread footing supporting a single centrally supported column but less common than square footing flagpoles. Instead of square, it will have a diameter and that will be sufficiently supporting your column which will transfer the load to the soil. Continuous spread footing or strip footing used to support the bearing walls. Two columns will be attached with a beam which is known as a strip and will have the footing below it, that is known as your continuous spread or strip footing. Combined footings when columns are located too close together for each to give its own footing. stack footing with a grade beam. It provides the necessary moment resistance in the external footing with an eccentric load and a more rigid foundation system. So these are your types of footing. First is your square footing. Next is your rectangular footing. This is your column. This is arrow shows the load which is on the topmost part of your footing here, and you can see here also this is the axial loading, and these are the loadings of the bearing wall on the continuous footing. This is your circular footing. This is your combined footing. This is your loading on the two columns, and two columns are resting on a single footing. This is your ring of column footing. This is your strip footing, strip or stack footing. The two columns with footings here having axial loading will be combined with your combined footing. Mat or raft foundation, mat foundations, raft foundations are very large, encompasses the entire foundation over individual spread footing. Spread the structure load over a larger area, thus reduces bearing pressure, provides much more structural rigidity, and thus reduces the potential for excessive differential settlements, is easy to waterproof, has greater weight, and thus is able to resist greater uplift pressure. So all these things, mat or rafting means it's just like a mat, lots of beam is projecting upwards, the column are lifted upwards from that beam and footing. It's just a slab beam combination at the base of your foundation. Now failure modes. There are three types of failure. One is your general shear failure, another is your local shear failure, and third one is your punching shear failure. So first is your general shear failure. This is your column. Here your footing is there. When you have such a footing failure, it will try to bulge out. Means this column will have the load like this, and this will transfer the load in this direction, and it will try to bulge out. This is your ground level, and the soil will try to move upward, and this is your bulging of the soil. So this bulging of the soils means heave in upward direction. So this has to be stopped. So if this happens, this type of failure is known as your general shear failure. Then you have to calculate load versus settlement, and if you give a tangent here like this, then what will happen? This will give you the total loading for required settlement. So this will give you load versus settlement. Here also, if you can see, this is local shear failure. So when you will, this load will come. So this will travel here also. So when this soil will try to go in upward direction, a light bulging will be there in local shear failure. So it is not so harmful, but you have to take care. So when you plot a load versus settlement diagram, so this will give you ultimate loading at 2 points, and this will give you the load versus settlement. At this QU, what will be your settlement, and this ultimate loading, what will be your settlement. Next is your punching shear failure. the bulging will not be there. There will be a direct failure under the loading of the column, and this will give you the QU versus settlement. So this is your load, will give you this load, and this will be your settlement. So first was your general shear failure, second was your local shear failure, and third is your punching shear failure, which was given by Vasic in 1973. So failure modes, a function of relative density and relative depth. When df by b, here there is df by b degree, and here you can have the relative density gamma d gamma. So when you are having a punching shear failure, you are having a local shear failure, you are having a general shear failure, whatever may be the loading, if you have a punching shear failure and density about 0.81 or here zero point 0.9, then what you have to do is you have to just project on this curve, and horizontally on the d by b ratio will give you the value. So B0 is B for circular diagram or square, 2B upon B plus L for rectangular fit. Ultimate load occurs at 4 to 10% of B for general shear failure, and 15 to 25% of B for local and punching shear failure. So you can see that there is a drastic change. When you are having a general shear failure, it is near about 10% maximum. But when it occurs local and punching shear failure, it goes to 15 to maximum 25%. So very critical is in the case of general shear failure. Bearing capacity, it is the load carrying capacity of the soil. So what are the basic definitions? Ultimate bearing capacity or gross bearing capacity, QU, it is the least gross pressure which cause shear failure of the supporting soil immediately below the footing. Next is your net ultimate bearing capacity, QNU. It is the net pressure that can be applied to the footing by external loads that will just initiate failure in the underlying soil. It is equal to the ultimate bearing capacity minus the stress due to weight of the footing and any soil or surcharge directly above it. Assuming the density of the footing, it is made up of concrete, and soil gamma, which is underlying the concrete footing, are close enough to be considered equal, then QNU will be equal to QU minus gamma into DF, where DF is the depth of footing. Next is your safe bearing capacity. It is the bearing capacity after applying the factor of safety, which is noted by Fs or FOS. These are the two types. So, safe net bearing capacity, QNS, it is the net soil pressure which can be safety and applied to the soil considering along only shear failure. It is given by QNS equals to QNU upon factor of safety. You know QNS means safe net bearing capacity, QNQ is net ultimate bearing capacity, and FS is your factor of safety. Next is your safe gross bearing capacity. So it is the maximum gross pressure which the soil can carry safely without shear failure. It is given by QS equals to QNS plus gamma into DF, where QS is safe gross bearing capacity, QNS is the safe bearing capacity, plus gamma is your unit weight of soil, DF is your depth of footing. Allowable bearing pressure, it is the maximum soil pressure without any shear failure or settlement failure. So this is your Q, the load on the column, this is your ground level, this is your footing, this is your DF, which is depth of footing. Then this Q is given to you as DF and total unit weight of the soil here present in this area. Children bearing capacity equation. QU is your ultimate bearing capacity, which is stress. QA is equal to allowable bearing capacity, which is given by QU upon factor of safety Fs. So if you are having the column with load P here, you are having a footing here with weight B, distributing the load to the underlying soil. This is your ground level. So this is your depth of footing. So what will happen? Under this will give you first punching shear, then the load will try to go in this direction. Okay, so it will travel radially. So when it travels radially, it will become curve here, and again it will become a straight line here. So if you give the names, this is A, this is D, E, H, and J. Here also C, D, E, G, and so for cohesion, friction angle is by phi. This angle is your 45 minus pi by 2. This also 45 minus pi by 2. Corresponding this angle will also be 45 minus pi by 2. Here also this will be a 45 minus into dS. So is the ultimate bearing we need to calculate. One is your Okay. So general bearing capacity equation, which is given by Carl Terzaghi, is QU equals to CNC plus QNQ plus half gamma B and gamma, where CNC here is your cohesion term, QNQ is your surcharge term, and half gamma B and gamma is your friction term, where gamma is equals to Q equals to gamma dF, where dF is your depth of footing. NC, NQ, and gamma are your bearing capacity factors based on alpha equals to phi dash and based on alpha equals to 45 plus phi by 2. General bearing capacity equations, bearing capacity factors and other influential factors. To consider the influences of the shape of foundations, embedded depth, and inclined load, the following form of equations has been suggested. So look how beautiful and big the equation is. All the factors you have to calculate. So here QU equals to CNC, FCS, FCD, FCI plus QNQ, FQS, FQD, FQI plus half gamma B and Q, F gamma S, F gamma D, F gamma I, where it is given by different scientists. So first NQ and gamma and NC were given by these scientists, NC by Pandrel 1921, NQ by Resisner 1924, and gamma by Caquet and Carissel 1953 and Vesic 1973. So last was given by Vesic, so we need to consider that. So these are the bearing capacity factors. When you get the phi from direct shear test and C, then this C and C and Q and gamma, these are given by Vasics and Terzaghi for calculating the bearing capacity of the soil. So from phi 0 to 50, the values for this bearing capacity are given, and you have to put the values in the given formula of QU and calculate the bearing capacity of the soil, which is used to design the footing of any column. Next is your shape factor given by DBN 1970. So FCS is given by 1 plus B by L NQ upon MC. B and L are width and length of the footing. FQS 1 plus B by L tan phi dash. F gamma S 1 minus zero point 0.4 B upon air, where L is the length of foundation. L is always greater than B. So depth factor Hassan 1970 was given for DF by B less than or equal to 1. Then FCD equals to 1 plus zero point 0.4 DF upon B. FQD equals to 1 plus 2 tan phi dash 1 minus sin phi dash square df upon b. F gamma d equals to 1. For df by b greater than 1, FCD 1 plus zero point 0.4 10 raised to minus 1 df upon b. FQD equals to 1 plus 2 tan phi dash 1 minus sin dash square 10 raised to minus 1 df upon b. F gamma d equals to 1. All these formulas you have to keep in mind. while solving the numerical for calculating the bearing capacity of the soil. Inclination factor was given by Hanna and Meroff in 1981. FCI equals to FQI equals to 1 minus beta upon 90 square. F gamma equals to 1 minus beta upon phi dash square, where beta is the inclination of the load of foundation with respect to the vertical. IS code method, whenever you are going in market for any design in the field, you have all the values of GT1. By doing all your practical work, you get all the values. You get the value of C, you get the value of gamma, you know the tentative width of the footing, weight of the soil, everything if you get. Then with the help of IS code 6403/1981, you have to calculate the ultimate bearing capacity of the soil. And that ultimate bearing capacity of the soil is known as your safe bearing capacity of the soil. With respect to this IS code method, bearing capacity is calculated, and for that bearing capacity, you have to determine the footing calculations or design the footing. So Q NQ equals to C NC SC DC IC plus Q NQ minus 1 SQ DQ IQ plus zero point 0.5, which is half gamma B N gamma S gamma D gamma I gamma W dash. So what are these factors? We know C and C, we know Q and Q, we know zero point 0.5 gamma B and gamma. So what are S, D and I and W? Let us see. So the factor W dash takes into account the effect of the water table. If the water table is at or below the depth of df plus b measured from the ground surface, W dash equals to 1. If the water table rises the base of the footing or above, W dash equals to 0.5. If the water table lies between the value is obtained by linear interpolation, the shape factors given by Hassan and the inclination factors given by Wessex are used. The depth factors are given below. So DC, this formula, DQ and D gamma, this formula, but when phi dash is less than 10 degree. And if it is greater than 10 degree, then D gamma and DQ are given by this calculated by this formula. When the soil is cohesive, then there will be no Q and gamma. There will be only C, NC and these factors. So where NC will be equals to 5.14 and SC, DC, IC are respectively shape, depth and inclination factors. Effect of water table influence on Q and gamma of the bearing capacity equation. So you can see the diagram. Here you can see there is column. This is your footing with width B. This from base to the top of ground level you have DF, and you are having a water table somewhere here. And one water table, if the case is the water table is here, first case, then this will divided into two different halves. This will be your D1 above the water table and this will be your D2 below the water table to the base of the footing. If the case is 2, the water table is below the base of the footing, then from base of the footing to the ground level it will be DF, and from the base of the footing to the water table then it will be D. And here the soil will be saturated unit weight. So if first case D1 is less than DF, so this is your D1, when it is less than DF, then you have to calculate Q and Q by this formula and gamma and B gamma by this formula. Second case, if 0 less than equal to D less than equal to B, and it is this condition, then Q and Q by this formula, and gamma by this formula, where gamma T is the total unit weight of the soil, gamma sat is the saturated unit weight of the soil, and gamma W is the unit weight of water. And third condition, when D is greater than equal to B, there is no effect. When D is greater than B, no effect will be there, no harm, moderately not harmful that will be to the footing. So no seepage force is there. Kindly have a look on this effect of compressibility. For compressible soils, you have local shear failure. For example, loose sands have low relative density. Then shear triaxial test response and load settlement curve for loose soil with those for dense sand. You can see two diagrams. So this is your effective strain, this is your stress. If this is your curve, then it will be the dense soil. If this is your curve, then this will be your loose. Then if you plot a curve between your load or pressure versus soil or settlement, then this is your general shear failure. This will be your local and punching shear failure. So this curve will give you the ultimate load versus settlement. So this Terzaghi recommendations use C and phi reduce shear strength parameters in bearing capacity equation. And this is the condition when there is reduced condition in bearing capacity, then C can be calculated by 2/3 of C dash, and phi can be calculated 10 phi equals to 2 by 3 10 phi dash. So this was all for today. If you have any queries, you can let me know. For attendance, kindly give your attendance in chat box. In next class, we are going to start with the numericals. So kindly have your notes with you. Thank you.